Well, good morning, everyone. Maybe I shouldn't say good morning. We've actually have people here today from really kind of all over. So it's as far away as Bahrain. And we'll get started here in just a second. I just wanted to take time to welcome everybody to today's webinar, where our topic on our road to continuous improvement is mechanical integrity. So just to kind of let you all know, and I'm not going to spend a whole lot of time on this today because we do have a subject that I know a lot of you are interested in and want to get some more information about, etc. But just kind of let you know where we've come from the beginning. We've actually working our way through all 14 plus elements of PSM, OSHA's PSM. And thus far we went through the management systems and really talked about the importance of documenting your management system so that you know who should be doing what. We talked about employee participation, we talked about process safety information and process hazards analysis, operating procedures, training, and contractors, and pre-startup safety review. And all of these first elements really have to do with design. If you think of a greenfield design process, these are all of the things that you would have to go through to design that process and to start it up. From what we're going to be talking about today is really maintaining those systems the way they were designed and intended to be maintained. So without spending a whole lot more time on this, we're going to go right into mechanical integrity. So as always, we always touch on the actual codes and Federal Register or the regulation itself. And when we talk about mechanical integrity, we're really talking about pressure vessels, storage tanks, piping systems. We're talking about emergency shutdown systems, controls, monitoring devices, sensors, alarms, and interlocks and pumps, compressors, the like. So really, oftentimes I tell people if the HAC or the hazardous chemical can come in contact or is controlling that hazardous chemical in any way, it would fall under mechanical integrity. So just about everything that shows up on a P&ID plus a little bit more should be in your mechanical integrity program. So really there's several paragraphs within this code. The first really talks about written procedures. So you must have a written procedure for all your mechanical integrity tests and inspections. You may hear me throughout this webinar today talk about and use the acronym ITPM. So ITPM really stands for inspection, testing, and PM or preventive maintenance. The next thing in the code is talking about training employees involved in maintaining the ongoing integrity of the process. So really, it's no different than an SOP. We create an SOP. The analogy here is written procedures for testing and inspection. When we create the SOP, we must train our operators on that SOP. Same way here, we create the procedures for doing ITPM. We need to train our employees that are executing those tasks on those specific procedures, along with the hazards that are associated with that work that they're in those tasks that they're will be doing. The next thing here is J3, and it talks about the fact that the procedures, and actually this is a misprint, this is another J3. So really I need to go to the next one. J4 is inspections and tests. An inspection and test must be performed on process equipment, and they must be in accordance with recognized and generally accepted good engineering practice. And really that can be not only the rega gaps like API, ISA, IIR, etc. But then there's also the OEMs or the original equipment manufacturers requirements as well. And a lot of the systems that you put in, especially detectors, and then some pumps, for example, and compressors, all have OEM requirements that you would have to follow as well, that may not be written into any of those other consensus standards that you would normally use. So J5 really talks about equipment deficiencies. And this one here, oftentimes, I know when I was working with OSHA for 5 years, this one was often miscited, or more so than it was cited correctly. And really, when we're talking about deficiencies, we're talking about those things that we have discovered as part of our ITPM task. If there's deficiencies against the design, then that would fall under a J5 type citation or required to be addressed via a J5. The last thing, and this is the thing that also often gets overlooked as well, is talks about the construction of new plants and make sure that the appropriate checks and inspections have been performed. This is where that PSSR that you conduct should fall into place, and making sure that that is done correctly to make sure that your mechanical integrity inspections are done correctly as well. This is where we also pick up your spare parts and making sure you have those spare parts in your stores or readily available, and making sure that those spare parts actually fit those design criteria that you laid out in your PSI. So really, what's the purpose of intent of this particular element? Well, one is to maintain the equipment within the design intent, or PSI. So if we've done a good job of developing our process safety information, then it should be easy to understand exactly what we need to do in our mechanical integrity programs. It's a simple thing. Make sure that we maintain it to the original equipment design. It's also is to establish ITPM requirements, REGAGAP. What REGAGAPs or what policies, procedures, and programs are you going to follow? Oftentimes I get asked the question, well, do I have to follow API? Do I need to follow IAR? Do I need to follow ISA requirements? And the answer is no. You can create your own. Your company could create your own policies and procedures for MI. The issue is you need to make sure that they're just as stringent as those other codes and standards, and to make sure that you comply with the minimum requirements. So when you look at IAR, you look at API, you look at ISA, these consensus standards are the minimum requirements, and the key word there is minimum. So oftentimes I've been called as a knowledgeable witness in different cases, and I often get asked the question, did they follow this code and standard? Well, I would say yes. Well, then the next attorney will come up and have me read a sentence in the API standard or one of those other standards where it talks about the minimum. So you said the company did the minimum that they needed to do. Never comes across well when we just do the minimum. The next thing is establish an ITPM frequency. Well, I missed the written procedures, making sure that we create those written procedures for all of our ITPM tasks, and then establish the frequency. And we're going to be talking about the frequency and what is the right frequency as we go through this. And then providing the technician training that they need. If the technician is going to be performing these tasks, make sure that they have the skills and knowledge that they need to be able to execute these tasks. And then, of course, methods for correcting deficiencies. We need to make sure that we're creating those methods to address those deficiencies as we come across them. And then, of course, ensuring quality control. New equipment installations are per REGAGAP or to the OEM requirements, and the replacement of existing equipment is to those same standards. Oftentimes, I will get asked the question about MOCs and should I do an MOC on this or that? And it really comes down to design intent for sure, but also you need to go beyond that. You may have a replacement in kind that truly is a replacement in kind, it's almost identical, but there's mechanical integrity things that we need to address in that installation as well. So maybe in those cases, an MOC might be required. And when we get to the management of change element, I hope you'll join us for that, because we'll talk about things like that in depth. So where do we go wrong? Here's where we see the gaps. And really, it's one of the top 10 and actually probably top 1 for OSHA PSM citations. When you remove all of the other the fluff that kind of goes along with some of these citations, it really comes down to mechanical integrity as being the #1. And really, we've done here at PSS, we're coming up on 300 PSM audits. we have yet to do one audit where we've not had MI issues as some of the findings. So MI is a big issue, and it continues to be one. And it's for a couple of reasons. One, PSI is not correct and up to date. And if PSI is not correct and up to date, then your MI will fault sometimes as well. So we need to make sure that our PSI, our process safety information, is always correct. So some of the reasons we have found, and what are some of these findings that we normally find? One is failure to test critical safeguards, and we're going to talk about that here in just a minute as well. It's failure to test and inspect piping and vessels. And these are just failures to do it, period. It's not whether they did them right or wrong, it's whether or not they did them at all. So we still find many instances where critical safeguards, piping and vessels are not tested at all. Deficiencies are not addressed. And this normally happens, oftentimes we see when a third party is doing MI inspections on piping and vessels. They may do external visuals, they may do UT thickness readings, and they may come across a deficiency, but the deficiency never makes it to any action. It winds up in a report that never is developed into an action that is addressed anywhere. The other thing that's real common is no written procedures for testing and inspection. And this doesn't go into the fact that we often see written procedures that are incorrect. In other words, how they're actually executed, especially when it comes to critical safeguards and critical instruments. How those tests are conducted is just as important as doing the tests themselves. If you don't do the test correct, then you may as well not have done the test at all. So making sure that those tests are done correctly is very important. Also, failure to follow REGAGAP. For example, testing frequency. If you follow IAR, if you follow API, they have set frequencies for those tests and inspections to be done. If you're following API, for example, it requires that you develop the remaining life and rate calculations or corrosion rate calculations. That's, if you don't do those, that's failure to follow REGAGAP. Also, is relief valve inspections indicate following but no follow-up action. I don't know how many times I've looked at third-party relief valve inspections, and they will indicate failing or fail to pop, or some other indication within the report itself that would indicate to me that there should be some follow-up work done. Follow-up perhaps to increase the frequency so that the next time that valve is inspected, it doesn't have those fouling issues or it doesn't have that damage that was indicated in the report. The other thing I see quite often is companies or facilities will claim it's risk-based or RBI. They fall under the risk-based or RBI inspection program, yet have no historical data to justify getting to that program. As most of you may know, that in a risk-based inspection program, we need to establish some history. We're going to do inspections based on risk. We need to understand the risk. We need to understand the modes of failure. We need to understand where we are at historically in determining what kind of risk do those systems pose to our health and safety of our employees. So included in MI are pressure vessels and storage tanks. Piping systems include piping components, and that includes valves. Maybe if the filter is installed, but that housing isn't large enough to fall under ASME Section 8 or a vessel code, they may fall under the piping code and would have to be inspected and tested accordingly there. Emergency shutdown systems, things like ESDs and permissives. If there's some permissives that are involved in your emergency shutdown, those would have to be included as well. Controls, including monitoring devices, sensors, alarms, and interlocks. Pumps, and pumps includes compressors, etc. And then all P&ID components, essentially. So when it comes to MI for piping and vessels, one size does not fit all. Not all process industries obviously are alike, and modes of failure are different. For example, if we look at the petrochemical industry, internal corrosion is very common. So depending on the materials that they use, acidics and caustics and materials can attack the metal surface itself, not only corroding the surface, but also have external cracking failures as well, especially in and around equipment that has, for example, in and around cooling towers, et cetera. We see a lot of cracking. We see a lot of external corrosion as well that has to be addressed. Also, within the petrochemical industry, we have a lot of corrosion under insulation, or CUI. This is a very big issue in a lot of refineries, a lot of chemical plants that especially have carbon steel. But just because it's carbon steel doesn't mean they're not going to have issues with other metals as well. In the refrigeration industry, especially in the ammonia refrigeration industry, we see a lot of corrosion under insulation is their main mode of failure. You can also have external cracking and failures, especially around condensers that have stainless steel piping. Also, within that industry, you have a lot of piping vibration and hammer that would have to be addressed as part of your mechanical integrity programs, and making sure you're looking for these particular items as part of your external visual to determine whether or not these mode of failures would be present in the industry that you're working in. Heat exchangers is another thing. It's tubes, tube sheets, and plates. A lot of times, just about every industry, doesn't matter what you're in, you're going to have heat exchangers. All those heat exchangers have tubes, and they have tube sheets, and they have plates, et cetera, depending on the type of exchanger you have. Every one of those exchangers need not only external UT inspections or external visual inspections, but they also need to be examined. The tubes and tube sheets and the plates need to be examined at some frequency, looking for any failures. Oftentimes I will get told, well, you know, why do we want to inspect those tubes? You know, really we're trying to keep material from getting outside and having a loss of a containment to the atmosphere. And, well, we know that that's not always the case. A lot of times we can actually look at a facility's PHA, and within their PHA they address tube failures, and hopefully they've addressed tube failures or tube sheet failures or internal failures of heat exchangers. And sometimes that material, the highly hazardous chemical goes into cooling tower water. It may go into chill water. It may go into other secondary media that is even more hazardous than if that material was to leak to the atmosphere. So those things need to be addressed as well. So just keep in mind that different rega gaps may apply. So it doesn't matter what industry in, you can still select a rega gap that may not necessarily fit your industry, but you need to either have your own, like I said earlier, or use one of the already agreed upon consensus standard. Risk is different as well, and that's the other thing that we need to remember. We'll talk a little bit later on about risk-based inspections, or RBI, but the key word there again is risk. Risk is different for every facility and maybe for every industry. For example, if you're a gas plant, or you're in a gas plant in the middle of West Texas or the middle of Canada, you may not necessarily have the higher risk that somebody who has that same gas plant that's located in downtown Houston or downtown Calgary or somewhere else. Those risks change, and your risk tolerance change. So therefore, your inspections and tests based on risk need to change as well. So MI on release systems include, and we see this quite often, is pop testing in place only. Well, when you do a pop test in place only, all you're looking at to see whether or not the actual device lifts at the proper pressure. Doesn't tell you whether or not the relief device has internal damage that would limit the amount of material or capacity that could actually, that relief device could actually attain should it be called upon for use. There's no inspection of the inlet and outlet piping. Remember, one of the modes of failure of relief devices is inlet outlet pipe failure. So a pop test in place only doesn't give you that information. We need to review bench and field inspection reports. So pulling that relief valve out and doing an internal inspection of the relief device itself, plus looking at the internal and external piping to make sure that there's no fouling. And if there is fouling, then we have to address those and make adjustments to the inspection frequency that we currently have. We need to make sure that the device will operate on demand. That's the whole reason we do ITPM on relief devices, is to make sure that they respond when they're needed and respond in the correct way. And that's at the right set pressure and at the right capacity. The other thing that often gets overlooked in relief systems is flares and related equipment, whether that's knockout drums, whether that's the piping itself on the relief system headers and piping, including the drains, etc. So doesn't matter what industry you're in, even ammonia refrigeration have common headers that these relief valves relieve into. They may go to atmosphere from that point, or they may go into another device, a destructive device, or a device that can actually capture the toxic and keep it from going to the atmosphere. All of these would have to be tested and inspected and accordingly. Again, may not have a reg gap that actually fits your particular industry when it comes to inspection and test of these devices. That doesn't mean you don't test and inspect them. You have to develop your own inspection and testing to fit that need. Also, making sure, for example, if you have pilot flares, looking at making sure the pilot system is working the way it needs to. And maybe if you have steam injection, making sure that that steam injection is working. A lot of times if you see in an industry, you see a lot of smoke coming out of a flare, you know you probably have issues with steam, and smoking flares normally are a direct result of not enough steam for those particular items. Not always, but most times. Also making sure the blowback systems are working correctly and making sure we inspect and test those systems to make sure that they work. There are a number of things within flares that we need to inspect and test. Again, looking at the OEM manuals for those particular devices can help you decide and determine what inspections and tests that need to be done. So let's talk about critical instruments next. Every facility, doesn't matter what industry you're in, you're going to have critical instruments. The question is right now, can you certify that the critical controls have been tested and inspected? The first thing that you need to know, obviously, in order to answer that question, what are the critical controls? And we're going to talk about that in just a second. But if you don't know what those critical controls are, more than likely they're not tested and inspected. Can you certify that the critical controls have been working as intended or designed to work? Again, what do we need to know in order to determine that? We need to understand what the PSI is, or the process safety information that is associated with those. If you cannot look at your process safety information and determine how a system, a critical control works, then your process safety information needs to be updated. If your process safety information is incorrect, then I will almost guarantee the inspection and test isn't going to be correct as well. Everything requires process safety information. So if my process safety information is incorrect, as we stated, then your inspections and tests are going to be less than desired as well. Also, it requires you to look at your PHA, your process hazards analysis, to determine what some of those critical instruments are. And we're going to take a look at a PHA segment here in just a sec to see what information we need to be pulling from there. We need to make sure that when we're looking at a PHA, we're looking at the hazard scenario, what we're trying to avoid. If we're trying to avoid a catastrophic failure of a vessel, then that is a critical safety device. So, and we can all, I think, agree that if there's a safety consequence that is identified in the PHA and we have devices that keep that from happening, then those devices would be critical instruments and should be considered critical instruments. We need to make sure that the device will operate on demand. Same way we talked about relief valves a second ago, we need to make sure that our critical controls operate when they're demanded to do so. So let's look at some PHA safeguards. First of all, I just want to state that not all safeguards are critical. And what I mean by that is you may have a safeguard that's listed in your PHA, and see if I can turn on some annotation here. So if we just had a safeguard that just dealt with environmental and economics and no safety, forget about that line that says safety up there. If this safeguard was just to keep environmental or economic issues from occurring, then we may not list this as a critical safeguard. However, when we look at these particular excerpts from a PHA, the S stands for safety. This is a critical or a severity level 4 and a likelihood of 2. The severity level 4 itself would indicate that anything that I have over on this side is safety critical. So if we look specifically, we've got a relief valve. We know that the relief valve would be safety critical. This happens to be on a truck, so nothing we can do about that. We also have a high level switch here. That would be a critical control. So we'd want to make sure that that critical control is, first of all, in our process safety information, and we understand what triggers that safety device. We'd want to make sure what is the output of that safety device. So in other words, what is the input and what is the output, and at what level or what trigger point or set point these things should occur. All of that information should be in your PSI, your process safety information. If it's not, then that's the first requirement that we need to have. It should have never showed up on the PHA to begin with had it not had the proper PSI, but that doesn't necessarily mean that's not the case at your facility. A lot of times we as part of our compliance audits, and I know we have some folks on here today that have been a part of one of my OSHA audits when I worked for OSHA, so they would understand. One of the things I always would do is go through the PHA and pull specific safeguards out and then ask for the inspections and tests on those devices. So if they could, and of course I would ask for the PSI in the process. So a lot of times I wouldn't receive the PSI, but I might receive a test or inspection result. So there could be 2 citations there. If you had the PSI, that would be fine. If the PSI didn't match the inspection and test or the actual what was actually in the field, that could still be a citation because it was not accurate. And then of course the test itself would have to reflect that it was actually tested and inspected at a frequency, typically annually, but we're going to talk about frequency here in just a second. But making sure that you look at your PHA and define what those safeguards are is important. Let's see if I can clear this out. So if used for risk mitigation, they must be in tested inspection. So any safeguard that's listed over there in the right-hand column, if it's used for some mitigating some of those risks or those consequences that we see here, then we need to test and inspect those. Now the issue becomes, how often do these need to be inspected? If you're lacking data to support the frequency, then it defaults to annual. So if you have information that says if I test this every 2 years, I can achieve my risk reduction that I want or desire, then you would be expected to test it every 2 years. But without any of that information, then it would default to annually. Remember, your facility defined what risk is and its severity. So the inspector or the person that's doing the audit, the OSHA person, they don't necessarily are going to tell you what your risk is or what your severity is. You define what that is when you did your PHA. So if you define a system to have a safety consequence, then those safeguards would have to be tested inspection for you to achieve that reduction in that risk. If you use a generic risk matrix, then you may be over understating your risk. Like we said earlier, that the risk is not the same for everyone. And for example, if, again, using the example of being out in the middle of the country versus being in the middle of a downtown area, then your risk would have to be determined appropriately. So that you may have a safety level of 3 on something that within the country, out in the rural area, that might be a safety level 2, etc. Okay, so MI on pumps and agitators and blowers, and this is something that quite often we don't see get inspected because people will say, I couldn't find a rega gap. But if you look at the manuals on most pumps, agitators, blowers, etc., they will have a maintenance section that's in the back that it will specifically outline those items that you should not only be PM'd, but those inspections and tests that you may be required to do on some frequency. Maybe it's monthly, maybe it's every 6 months or annually. So following those guidelines, if you don't have yours in place already, or if you do have your own MI programs in place, making sure that you go back to those OEM manuals to pick up any information that you might have left off in your programs. It's a good opportunity to verify your PSI to make sure that all your process safety information is correct and up to date during those inspections and tests. I don't know how many times we've actually found that, for example, the pump, especially when it comes to centrifugal pumps, where the impeller size has been changed, and during the PM where they've actually opened the pump and inspected, actually found that the impeller was larger than the PSI that had actually indicated it was. This has several ramifications for you that are aware that this could affect relief devices, making sure that they're sized correctly, but it also could have other effects downstream in terms of your process safety information and your safety systems as well. So making sure that we use that opportunity to verify our PSI is important as well. So the key to MI, and especially when it comes to pumps and agitators and blowers, obviously in everything, is to keep equipment running, and it's to avoid unplanned shutdowns. Unplanned shutdowns are most dangerous thing in most facilities. So some additional MI coverage that we want to look at is employee alarm system, making sure that those alarm systems work as intended. Also structural and civil systems. That includes foundations, anchor bolts, supports, pipe hangers, pipe bridges that support the weight or the movement of equipment or otherwise included in the MI program as well. Also, you may have utilities. Service systems or components for equipment included in the MI could be electrical power, air, steam, nitrogen, all kinds of different systems that could be included. Best place to go look to determine whether or not any of these systems fall or should be falling under your MI programs is the PHA. If you have consequences that can result, hazardous consequences that can result as a loss of one of these utilities, then that utility would have to and must fall under your mechanical integrity program as well. So let's just talk briefly about MI procedures. Again, they must be written, they must be detailed and specific. They should include the test parameters and what is being tested. And of course, we already talked about you may use the original equipment manufacturers, the OEM procedures for testing, and that's perfectly fine. You don't need to copy and paste those. You can just reference those particular procedures, making sure that you have obviously a copy on hand. Must train your technicians on the task and the procedure, and that training must be documented, including a verification of understanding, making sure that they understood the training that they were provided. So now let's go into documentation itself. What documentation must you have for your mechanical integrity? Well, we can go right to the code and standard itself. It says for each process equipment, You must have the functional item, a description of the test or inspection or PM, and of course it must be tracked throughout your PSM program. It must comply with recognized and generally accepted good engineering practices, or REGAGAP. There should never be a pass-fail result only. We still see quite a few facilities that would go into they at the end of the inspection and say passed, and really nothing in there to determine what they actually looked at. Did it fail? Did it pass the first time, or did it pass the second time, et cetera? Did they find issues in between there, but they fixed them and then tested it again and it passed? All of that's historical data that would get lost in a pass-fail type result. Instrumentation drifts. I don't care what industry that you're in, all industries have devices, instrumentation, et cetera, that drifts. One of the things that we came across not too long ago was in ammonia refrigeration facility where the testing of high pressure cutout or high pressure interlock to shut down the compressor on high pressure was not working. Well, when we started asking questions as to what was going on, quickly we realized that the inspection that was being done on the actual instrument, in this case the pressure transducer, was not being done properly. Obviously, there are some issues I know with the REGAGAP for that particular industry on determining how to calibrate a high pressure transducer, which aren't exactly right. Those transducers can have hysteresis. The hysteresis is meaning that essentially the device isn't linear anymore. So every milliamp that you receive, you expect linear response. Well, not all instruments stay linear, and that's one of the things that you're testing as part of your calibration that you should be doing at least annually, or more frequently or less frequently, depending on the criticality of the device. We, again, are looking for failures on demand in our documentation. So if we're testing the instrument correctly, we may have situations quite often when they're tested correctly, they actually fail to do what they were designed to do. That would be considered a failure on demand. For example, if you were to test a pressure interlock that would shut down the compressor when the pressure gets so high, if you actually impose that pressure on the device, would it shut down the compressor? If it did not, that would be a failure on demand. Same way with a level. For example, we imposed a level on the device, not reset the set pressure or set level, et cetera, but actually impose that level on the device itself, on the input device. Would it actually shut down what it was supposed to do, or execute the steps that it were supposed to do when you got to that particular trigger point? If those things do not happen on demand, then we need to adjust the frequency of tests until we're getting results where they operate on demand each and every time. We must document that the equipment complies with REGAGAP. Now, oftentimes when we come to this particular element within PSM, we ask, well, what does it mean it complies with REGAGAP? What it means is essentially, if we look at our process safety information, once we completed our inspections and tests, does that equipment now comply with REGAGAP? Does it still comply with the original equipment manufacturing requirements? Does it comply with ASME code? Does it apply to AAR code, et cetera, depending on your chosen REGAGAP? So let's talk about vessel inspection, pipes, tanks, and piping in terms of documentation. So online inspections, normally those are UT inspections, and they may include a external visual inspections. What do you do if you have brand new equipment installed? Does that new equipment get installed right away, or do you wait until the next round of UT inspections before you test it? What you should be doing is inspecting it when it's put in place. Again, we talked about earlier the fact that some things are replacement in kind and direct replacement in kind. However, you have baseline information. You also have information on UT inspections that the next time a person goes out there and takes that reading, if that has been replaced during in the last 3 years, and then they see a larger number, then that should indicate there was something going on or something has changed. However, if we make those changes early on and get those new readings as soon as that piping or vessel is installed or tank is installed, the easiest time to do it is before it's brought into service. Then we have those baselines that we can use in the next round. Certainly, you can use the historical data that you've obtained to determine the corrosion rates, assuming that it's the same material itself. A lot of times, online inspections, UTs, for piping, vessels, and tanks are frequency-based. So many years we need to do inspections and tests. Or they can be risk-based and based on the risk and modes of failure. Again, it's important to understand that those modes of failure are going to be different for every industry. You also have internal inspections. So you may have vessels and tanks that require internal inspections, and they do if you're following REGA-GAPs, as well as external visual inspections that must be done. Also, you can be subject to corrosion under insulation or CUI issues. UT inspections or visual inspections under insulation, not going to help you a whole lot. And we see this quite often in the ammonia refrigeration industry, where their main mode of failure of piping and vessels is external corrosion or corrosion under insulation as well. A lot of times you'll see them drill the hole just like they would in the other industries to measure thickness. Well, that's like trying to find a needle in a stack of needles, you know, because your mode of failure in the ammonia refrigeration industry is going to be corrosion under insulation. So looking at a 2-inch hole in the wrong, especially if you're looking in the wrong places, you'll never find that corrosion issues. You need to make sure your inspections and test plan coincide with your modes of failure, to make sure that you're looking in the right places and doing that in a way that would reveal those issues and those risks. Also, must do your long and short-term corrosion rates. So if you haven't calculated your corrosion rates, long-term is more than one reading. Short-term is typically 2 readings. I'm sorry, long rate is more than 2 readings, 3, 4, 5, etc. Short-term is normally just 2 readings to give you some idea what your rates are. You can also use historical data for establishing your historical or establishing your corrosion rates and remaining life. You can only use that historical data, however, if it's relevant to the process that you're actually running. For example, ammonia refrigeration historical rates, if we're looking at UI or UT data, all ammonia refrigeration systems are basically the same. However, if we're looking at an oil and gas application, for example, not all gas plants process the same type of gas. For example, if your inlet gas in a gas plant contained some H2S, then your corrosion rates would be different than a facility that handled no H2S. So we need to make sure that the corrosion rate history data that we use is comparable to what the process will actually see, and then you may be able to use historical data. Also must calculate your remaining life. How long before we have to do our next inspection? Is it going to be as per the API frequency, for example, or do we need to do half the remaining life based on our actual corrosion information that we've developed? So piping also has components that must have external visual inspections and also UT, and we must develop inspection protocol. Again, baseline, new, frequency-based, risk-based inspections, again, based on the mode of failure on piping can be used as well. So instrumentation includes not only external visual, looking for things like wiring connections, making sure valves are locked open or valves are locked closed, etc. There can be a number of things, making sure the tubing is not kinked, making sure that the wiring itself and cabling is well connected. All of these things are part of your external visual inspection. But we also must develop the inspection protocol just like we do piping and vessels. The frequency, of course, we can do RBI on controls as well, just as like we can do piping in other equipment. Again, it must be based on our risk. And of course, we can follow OEM requirements when they're applicable as well. So the next thing is really new construction, and we need to make sure that those modifications and changes comply with good engineering practices, codes and standards, and you really define what that code and standard is. Design and codes may be the newer versions, they may be older versions, and they're different for existing equipment. Making sure that they're installed and getting constructed in accordance with the manufacturer's requirements, and they meet all your internal codes and standards if applicable as well. And then of course, making sure inspections and tests and QA must be done. And normally that should be handled through your PSSR program. The other thing is making sure welder certificates, inspector qualifications are correct. Certified welders should be used in materials that they're actually using. So making sure the certificates match the material that they're actually welding on or are providing for you. Making sure welding inspectors are in accordance with Reg-A-Gap. Typically, you don't want the welder being the inspector at the same time. Those should be two different people, and you need to follow the appropriate Reg-A-Gap. But that's API 31.3, 31.5, etc. That's what you need to use. Making sure controls and instrument calibration testing are per OEM as well. And of course, like we said, making sure that the links are provided in your PSSR. I always tell people all the time MI is a big task. There's a lot in MI that we have to do and keep track of. And technology is a great tool that you can use to manage your inspections and tests and using the failure modes and critical ratings, etc. You can manage all your risk-based inspections, including documentation and risk profiles. And risk profiles are typically what we see is in your risk matrix and how you built those. It can manage and increase accuracy of your MI inspections and tests. So we can really hone in on where our risks are, where our problem areas are, where our issues from a MI standpoint are really located so that we can provide the resources that we need in the right areas. And of course, it allows us to manage those action items and follow up, to manage third-party inspections and reports. Like I said, this a common thing that we see quite often is third-party inspectors may come out and do your external visual inspections of your pipes or vessels, for example. They develop a nice report, they give you that report back, and somebody just may put it in a file cabinet or a folder, electronic folder somewhere, never look at the information that was in there in terms of what action items or what recommendations were really being made. So let's talk about some best practices here for a few minutes. And here's just a few things I want to make sure that we always look at when we're discussing mechanical integrity in your facilities is identify and document your chosen Reg-A-Gap. This can't be more important. You must choose or create your own. So making sure that you know what your Reg-A-Gap is so that when you have a regulatory body that comes into your facility or you have a third party that comes into your facility, they know what the Reg-A-Gap that you're going to be held responsible for meeting. If you don't choose, then you don't want the regulatory body to be choosing it for you, because they will probably most likely choose the one you really don't want them to use for you. Understand the requirements of your chosen Reg-A-Gap. So get training on what that Reg-A-Gap really involves, or get third-party assistance, get somebody to kind of help you develop your test plans and frequency, etc. Develop your Itpm plans and written procedures according with the Reg-A-Gap that you choose, and then Implement and establish history. So we talked about history of remaining life. RL is remaining life, and your short-term and long-term corrosion. If you don't have any history, then you're going to have to establish that by getting one and your initial reading plus at least one more to establish your short-term corrosion rates. And then evaluate what can be done via RBI. Once you've established history, once you've established your corrosion rates, remaining life, then look at opportunities to move to RBI. I recommend that just about every facility pursue a risk-based inspection program. Put your resources in the area where you have the most risk. Again, PSM is process safety management. The whole idea behind PSM is to manage risk. And so we need to understand our risk, and then we need to manage them. So if we have limited amount of resources, which we all do, then we want to put those resources to use in the areas that we have the highest risk. Review your PHA for safeguards and document all devices or controls that are designated as safeguards. Some may be critical and others less so, but document them. Non-critical may be inspected and tested less often than critical. Remember, risk mitigation. That's the goal here, is mitigating risk. So if you have a device that is critical, that is reducing a scenario that we don't want to happen, then obviously that is something that we need to test and inspect more frequently than those items that may not be as critical. Maybe it's an economic issue or environmental issue. Not that those are not important, but certainly from a health and safety of our employees, those are less critical. Develop an inspection and test plan for the controls. Again, making sure that the inspection and test plan meets the objective of the device. So making sure that our plan tests, for example, if it's going to shut down a device, make sure that that's the first thing that you do as part of your test plan, is to attempt to get to the trigger point that shuts down that device. Don't calibrate the instrument first and then come back and test it. I'll guarantee you that most every time, if that's what you're doing first, you'll never see whether or not it actually worked on demand. Another item is to review your PHA and document all devices or controls such as LEL, hazardous gas, flammable, oxygen detector, and burner management systems. Every one of these would have to be tested and inspected. Oftentimes what is a burner management system? And in fact, most facilities will have a burner management system in there. It doesn't matter if you're oil and gas, petrochemical, even some ammonia refrigeration facilities have boilers. Those boilers have burner management systems on them that need to be tested and inspected, especially if those boilers are in close proximity of your ammonia refrigeration equipment. Again, develop a test and inspection plan. This is where oftentimes we'll see OEM procedures are already in place. So the OEM has already laid out procedure for testing a detector, for testing a oxygen detector, LEL devices, and burner management systems as well. A lot of your burner management systems come with specific tests and inspections that must be done, and the frequency in which they must be done as well. If they don't, then you're going to have to create your own. I know a lot of, especially ammonia refrigeration folks, you will not, and probably don't even know what a safety instrumented system is, but a SIS. But I know if you work in the petrochemical industry, oil and gas refinery, for example, you will know what a SIS is. And a SIS is a specific type of instrument or control that is dedicated to safety critical operation. And they are developed in accordance with the Safety Requirement Specification, or SRS. They are tested based on the Design Safety Integrity Level, or a SIL. Some components are tested more frequently than others. For example, A lot of SISs will have input devices like level devices, pressure, temperatures that will have multiple inputs. So rather than just one that's reading 2 or 3 or 4, even 5 input devices to perform or execute a final element, whether that's close a valve, shut down a device, or something like that. The input devices may have to be tested, inspected, and calibrated every 6 months, while the output device only has to be calibrated and tested annually or every 2 years, for example. So they will all be different. All of them are designed at a testing rate to achieve a certain safety integrity level or SIL level. So making sure that you refer back to your SRS or safety requirement specification to find what that is, and then you must test and inspect those devices in accordance with those frequencies. No matter what, full functional test must be completed. So a full functional test is from the input to the final element or the output device. So let's talk about correction of deficiencies real quick. Deficiencies must be corrected in a timely manner. It must be done perhaps through a management of change process as well, especially if it has to do with fitness for service evaluations, etc. So if you have a vessel that is the UT thickness shows that it's less than the designed thickness amount, no matter how much that is, you must do a fitness for service evaluation on that. Either re-rate the vessel or go through another process to determine fitness for service for that device, especially if there is no corrosion allowance, it's outside its corrosion allowance already. Same way with piping, that must be done as well. Again, like I said earlier, institute a risk-based inspection program. In order to do that, you must understand your failure modes, understand exactly what your mode of failure is. Invest resources in the areas where the risk is the greatest. So you may have limited resources on inspection and tests. Put those in the area where you have the greatest risk. Not all facilities have the same risk as we talked about earlier. Not all facilities, we need to stop doing thickness readings when your failure mode is CUI. We need to start looking at our CUI programs to make sure that we're developing programs that actually are looking for areas where you can have the CUI, especially in your greatest risk. For example, you're not going to see a lot of CUI in areas that are always frozen solid. In other words, are always covered with a layer of ice. It needs to have, usually in that, there's a specific temperature range where you're going to see a lot of corrosion under insulation. Also, typically on systems that go through hot and cold, or you have insulation that gets wet and dry and wet and dry because of those temperature swings. A lot of times those corrosion of insulation issues are not going to be on the top of the pipe or the side of the pipe. They're actually going to be on the bottom of the pipe where most of the moisture actually accumulates. So we need to make sure we understand those modes of failure so that we're looking in the right places when we're doing our risk assessments. RBI is not a tool to reduce inspections, but rather to reduce risk. But when done correctly, costs are reduced as well. And we see this quite often when we develop good RBI programs for some of our clients. We see not only a cost reduction, but we also see risk reduction as a result. And they're spending their time and looking more frequently at areas of higher risk, and less frequency and time is spent on those with less risk associated with them. RBI is something that can be implemented in any process. So it doesn't matter whether you're a chemical, you're petrochemical, oil and gas, ammonia refrigeration, RBI is a good fit for any of these organizations. RBI also promotes knowledge in your process. as you begin to understand the modes of failure and how you can reduce the risk of those failures. A lot of times in my PSM training, I always emphasize and say this: knowledge is the key to reducing process safety events. A knowledge first begins with understanding what a hazard is. If you don't understand what hazards are and you don't understand the hazards in your industry or in your process, then you're not going to be reducing too many process safety incidents, because you don't understand what the hazards are, where they come from, et cetera. You're always chasing after the incidents and you're looking afterwards. But if you start to understand the hazards in your processes, then you begin to understand them and doing the PMs and doing the inspections and tests to prevent those hazards from occurring. So knowledge is the key to process safety. So what are some of the next steps? First, let's document and need to document your MI Reg-A-Gap and create your own to fit your process safety requirements. Review your PHA for designated safeguards. Develop ITPM plans based on your process and your risk tolerance. Create written procedures in accordance with your chosen Reg-A-Gap and ITPM plans. And of course, implement your ITPM policies and procedures. Review results, non-pass fail. We don't want to see those anymore. Review your results for adherence to Reg-A-Gap and policies and procedures. Don't ever assume somebody else is doing that. So if you have a third party that's doing inspections and tests for you and providing you a written report, try to get more than that, especially let that third party give you and sit down with you and talk about all of those deficiencies to make sure that you understand them and make sure that you're following up on any recommendations. Utilize technology to manage your PMs, testing, inspection programs to make it easier to achieve desired results. A lot of times we have a saying here at PSS, we want to make it easy to achieve those results. If you give somebody that's something that's hard to do, likelihood they'll never do it. But if you make it easy for them to achieve and make it easy for those things to get done, then they're more likely to get done. Also create KPIs or key process indicators that measure performance in your MI programs, making sure that you're actually reducing some of that risk. KPIs are a good way of doing that. Emphasize, and just like this whole webinar series is really talking about continuous improvement, remember, failure to address deficiencies can have catastrophic results. If you want to understand what those catastrophic results are, refer to your PHA and look at those consequences that can result if those things go wrong. Every one of those things that go wrong are MI issues that we can make sure in our programs we're addressing to make sure that they don't occur. Ensuring compliance can be overwhelming, and I'll be the first to tell you that. I spent 25 years in industry plus, so I know that MI can seem somewhat overwhelming, especially if you have not been involved in it for some time. But there's a lot to do, and often you have limited resources to do that. The consequences of not doing MI can be catastrophic. Some industries focus on not making chemicals, but rather using chemicals to ensure product quality, et cetera, like ammonia refrigeration. Ammonia refrigeration is just a utility in most facilities, a utility to make sure that products are kept cold, products stay frozen, et cetera. So in those particular industries, it becomes a little bit more difficult. If we're making chemicals for a business, then we want to make sure that the profits and everything else are where we need them. We often don't think of the utilities piece of it till we don't have that utility. Some industries' profit margins are affected by market. For example, right now, oil and gas, is suffering from a low market prices, et cetera. So as a result, a lot of times we lose resources or the resources get reallocated, et cetera. Regardless of the pressure, we still need to do the right thing. And that the right thing is making sure that we're doing our inspections and tests, et cetera. And and for the most part, we get it. We want to help you in any way we can. And that's kind of why we're doing these whole webinars, is to make sure that you're applying the resources, you know exactly what to do. We're trying to help provide knowledge, or at least a discussion of the things that can help you to achieve process safety, event-less environments, and making sure that you're staying profitable. One of the things that we do have, and I'm going to give a shameless plug out here today for joining us today for 2 p.m. for reducing that cost of compliance. So there's still some openings in that webinar, so we'd love for you to join us for that. We're going to be talking about just reducing the cost of compliance as it particularly relates to MI and other inspections and tests that we do. A lot of the information that we've talked about over the last several months on this road continuous improvement requires a lot of documentation, et cetera, and we kind of help explain that process and how we can make it easier. So recap, again, PSM elements, we kind of went through all of them up to mechanical integrity. We must maintain our process design. That's through maintenance, MI, hot work, and that's kind of what we're working on now. If MI fails, then we have potential to see the catastrophic failures we should have identified in our PHA. You can only maintain what you know. So knowledge is the key to process safety and continuous improvement. So again, we can't maintain processes and equipment if we don't know what the process safety information is on that equipment. So making sure we have that knowledge, like I said earlier, is important as well. So kind of open it up to questions now. If you want to go into the Q&A, certainly you can ask your question, and I'll try to open up here by voice as well, but you can certainly enter the chat question. Now, I'm going to start with the first question that I have up here. Can you elaborate on stop testing thickness reading when your failure mode is COI? It is our most important metric in determining action for maintenance or replacement for piping. And what I mean by that is essentially, and this particularly has to do with ammonia refrigeration piping. So oftentimes we go into facilities and they've drilled holes like they do in oil and gas and petrochemical, drill the hole in the piping, and then you 2-inch hole, take a reading in the pipe to determine, or the vessel, to determine whether they've lost any thickness or not. So if your mode of failure was internal corrosion, then certainly that would be a good tool that you might be able to use to determine a loss of metal, etc. But when you drill a hole for ammonia refrigeration looking for CUI, and you drill a 2-inch hole in let's even say every 1,000 feet of pipe, you're trying to find that specific location where you're having CUI issues. First, understanding the mode of failure is CUI. Second, understand where you may have that mode of failure occur. Again, as I said earlier, if that mode of failure occurs predominantly in a certain temperature range and moisture range, then we should be looking in systems those environments exist for that particular mode of failure. Also looking at larger sections. For example, if I had 1,000 feet of pipe, looking at a 2-inch hole isn't a whole lot in terms of area that I need to look at. So I want to look at more area than that, or better yet, using other tools. And there are a lot of other tools out there that don't require you to remove insulation, don't require you to drill a hole and damage insulation and moisture barriers. There's other tools that you can certainly use, and I would recommend. Not necessarily do you have to do the whole pipe, but do large enough sections to determine whether or not you have those issues. Now, once you've used a screening tool of some sort to determine if you have those issues, then larger sections may need to be screened as well, or looked at, or further inspections and tests need to be done. So hopefully I've answered that question. If not, feel free to send me an email. I'll give you some more insight and some more information on where you can go to get more answers on that. Any more questions? Let's see if I can open it up here just a second, see if I can get any. Somebody asked, is there a list of acronyms for PSM that can search online to stop, or a one-stop shop definition for PSM acronyms? How often are they observed PHAs having gaps during any of your audits? From a gap standpoint, see gaps all the time in PHAs. And a lot of times those gaps themselves are failure to address hazards. Also, a lot of times the safeguards that they list really have no bearing on reducing the risk of the consequence that they've identified. Or they've listed a whole bunch of safeguards for the consequence that they've identified, but then not tested or inspected any of those. And yes, there is a list of acronyms. I'm trying to think of, I can't just think off right offhand where those are located. But if you send me an email, we have a list here of acronyms that certainly we'll be glad to share with you as well. Somebody also asked, is there somewhere on your website where one can view past recordings? And right now we do record all of these, but we actually started to provide these as on demand, but then we got a lot of questions as a result because I think when we do them live like this, it gives everybody an opportunity to ask questions, and we can answer those questions really for everybody that's on the webinar. So currently, no, they're not available on demand, but certainly the next round, we're going to do them a little bit different so that they're available on demand as well. The next question I have, if it's a new construction, wouldn't the general contractor be responsible for those verifications? No, and yes. So if it's a new construction, it's your facility. It's your facility, and the facility has responsibility to make sure that all of the process safety information is not only developed, but documented, and you should be doing the PHA itself. So you should have somebody in that room, even as the owner of that facility, in that PHA to make sure that you understand the hazards, et cetera. So all of that documentation, all of that PSSR should be part of that whole process when you take ownership of that new process, even if it's a GC that's involved. And we get involved in quite a few new constructions where the GC is building or constructing the facility. We make sure that we've developed all of that PSI, PSM information as part of the handover to the owner. Make sure that all of their systems are ready to go. Next question, sorry I didn't, okay, all right. Yeah, somebody sent a link here, and I will, if you can't see that link in the chat, you can certainly use that for process safety information. And yeah, CCPS is a good guiding document for that. So any other questions? Must all vessels have internal inspections conducted? Again, if you're following your REGAGAP, and let's say if it's API 510, then internal inspections need to be conducted. Now, the frequency of those internal inspections will vary. Also, we're seeing quite often that the tools used for internal inspections, especially when it comes to vessels, there's a lot of tools now. Drones are actually used to go into these vessels and do those inspections, and you don't actually have to crawl in and do a vessel entry to do those inspections. So there's lots of tools out there, but yes, those inspections must be done in accordance with the REGAGAP or in accordance with your own OEM or your own, I'm sorry, not OEM, but your own MI inspections and test policies and procedures. And of course, if you have the history to indicate that you don't do those internals for various reasons, then that should be part of your MI program. Okay, any others? And thank you, Bill, for providing that CCPS online glossary. I appreciate that. I'll wait just a couple more minutes, and if we have no more questions, then we'll end this for today. And I want to encourage you to, if you can, join us at 2 p.m. For our reducing the cost of compliance or addressing cost of compliance, and then also our next road to continuous improvement is actually on hot work. This one will be somewhat shorter, but nonetheless, it's just as important. I've also put up here the link to our webinar this afternoon at 2 p.m. It talks about reducing the cost of compliance. So that link is there if you want to register for that as well. Yes, it's 2 p.m. Central Time. Just had somebody ask that question, and yes, 2 p.m. Central Time. Okay, you also have my email address down there. If you want to email me with any question, be glad to help with anything you have. MI is one of my favorite things to talk about. That is my background. I spent a lot of years in mechanical integrity, being a mechanical engineer. So certainly that's one of my passions, to make sure that all of our equipment and inspections and tests are done accordingly. So anyway, I want to thank you for being here today. Hopefully we'll see you at 2 p.m. today. If not, hopefully you'll join us for our next one on hot work sometime here in October coming up. We normally have one of these every month. Again, thank you, and have a great day. Appreciate you joining us today.